In my previous lecture, you were introduced to angular momentum and its conservation. The governing expression to describe its conservation comes from the following. The sum of the external torques that's exerted upon a system results in the change in the angular momentum of the system L with respect to time. So far you've seen angular momentum L as I omega. Think of angular momentum as a description of the total quantity of rotation associated with a system. When an external torque is exerted upon such a system, the total quantity of rotation changes. The conservation, however, of angular momentum results in situations where there are no external torques, or the sum of the external torques is equal to zero. So, if the sum of the external torques is equal to zero, then this derivative is equal to zero, and then therefore the angular momentum L is a constant. This situation is referred to as conservation of angular momentum. So therefore L is a constant. So if the sum of the external torques exerted upon a system is equal to zero, then the total quantity of rotation of that system doesn't change. So I demonstrated this at the end of my previous video by rotating on a stool, for example, with a bicycle wheel, and by using various weights and so on. I was demonstrating angular momentum and its conservation in those demonstrations. Let's immediately take a look at an application, and to do so, we'll take something from astronomy. So let's go ahead and copy down the following problem from astronomy here. Copy it down as I read it to you. Okay, so let's examine what happens with the sun. The sun eventually, about 5 billion years or so from now, will collapse and become a white dwarf about the size of the Earth. I previously have described the fate of the sun in the context of Newtonian gravitation in a previous unit. Okay, we will assume that no mass loss occurs in this process. What actually happens, however, is that the sun becomes a red giant beforehand, before becoming a white dwarf, that is, and it eventually sheds its outer atmosphere, forming what is referred to as a planetary nebula. The core of carbon, nitrogen, and oxygen that is left over at the end of this process is about the size of the Earth, and this is what is referred to as a white dwarf. For simplicity in this example, we will assume that there is no mass loss. And then in the second part of the problem, we'll assume that we can somehow crush the sun down even further, forming an object called a neutron star, which only has a radius of 10 kilometers. This will not happen in the case of the sun. The sun is not massive enough to eventually become a neutron star, but I previously have already described the formation of such a star in a previous lecture. Okay, let's go ahead and draw out the sun as it is right now. So here's the sun today. Like so, here's the equator, here are the geographic poles, and then we're given the following numbers in this problem. Currently, the radius of the sun is 7 times 10 to the 8th meters. The sun is quite large. We're going to refer to this as capital R naught. Okay, and then the rotational period of the sun is about a month. We'll call this capital T naught. This is equal to 30 days. And then eventually 5 billion years or so from now, after undergoing this process of becoming a red giant, a planetary nebula, and so on, the core of the sun that is left over, the white dwarf, is about the size of the Earth. Okay, so now 5 billion years or so from now, here's the white dwarf like so, equator and poles. But in this case, it's only about the size of the Earth. So the radius then, therefore, is that of the Earth, 6.4 times 10 to the 6 meters. Okay, what's unknown in this process is the period, capital T. Now, because there are no external torques exerted upon the sun as it undergoes these changes, this then means that the total quantity of rotation of the sun, the angular momentum, is a conserved quantity. So what I'm going to do is I'm going to write out an L equals I omega for each of these two scenarios here, and then set them equal to each other. So let's see what happens first of all with the sun as it is today. So I'll call this L naught. This is equal to the rotational inertia of the sun as it is today, multiplied by its angular speed. Now we're talking about an object that's a sphere, so then therefore we'll use the rotational inertia of a sphere as 2/5 mr squared. As we undergo this process, however, remember we're assuming that there is no mass loss. Okay, so then therefore, before the sun eventually collapses down, we have right here its rotational inertia, 2/5 mr naught squared like so, and then multiplied by its angular speed as it is today. Let's write that as 2 pi divided by the period, capital T naught. And now we'll do the same thing over here, 5 billion years or so from now when the sun eventually becomes a white dwarf. So let's call this L. We're going to refer to this as I omega. So this is analogous to, for example, a figure skater pulling his or her arms in while rotating. Basically, when that person does that, the rotational inertia decreases, and then therefore the angular speed omega is going to have to increase correspondingly. So in other words, the white dwarf here is going to be rotating much faster than the sun is right now. Okay, let's go ahead and write the I here as 2/5 mr squared, where the r is the radius of the Earth, and then multiply by omega, which is 2 pi divided by the unknown here, capital T. And now let's go ahead and set the two equal to each other and then just solve for capital T. Okay, so first of all, the sun as it is today, 2/5 mr0 squared, 2 pi, there we go, over capital T naught. This then equals the sun 5 billion years from now, 2/5 mr squared, 2 pi divided by capital T. And now a bunch of stuff cancels out, we'll cross multiply and then solve for capital T. So let's cancel out the 2/5 m and also the 2 pi from either side of the expression. Okay, let's clean up the expression a little bit, like so. And now let's cross multiply here and solve for capital T. So move the capital T to the other side, move the other terms over to the other side. Okay, so in doing so, capital T then ends up being r squared divided by r0 squared, and then multiplied by t naught. So let's go ahead and plug in the numbers as we have them right now. When I do, I'll end up with an answer for capital T in terms of days, and then we'll convert that. Okay, so let's plug in the numbers. So first of all, in the numerator, we have 6.4 times 10 to the 6th, and then we square that, divided by 7 times 10 to the 8th, square that, and then multiply by 30 days. So you end up with a pretty small number here in terms of days. There's only about 0.0025 days, but to put this into perspective, let's go ahead and convert this, say, into minutes. So to convert this into minutes, I'm going to multiply by 24 hours per day. Days cancels out. Let's go ahead and multiply then by 60 minutes per hour. Hour cancels out, and then therefore we'll end up with an answer here in terms of minutes. So times 24 times 60, and this ultimately comes out to be about 3.5 minutes. It's 3.6 minutes. Like so. As the rotation rate then of the sun when it eventually becomes a white dwarf. So these are some of the details here then therefore of what will eventually happen to the sun when it begins to reach the end of its life, when it reaches this stage. However, for more massive stars, instead of ending up with the core as a white dwarf, you instead end up with a much smaller core that's referred to as a neutron star. I'm posting some information about neutron stars and what are called pulsars in today's folder as well. So then therefore, if, for example, we can crush the sun down to the size of a neutron star, which only has a radius of 10 kilometers, ultimately then what will be its rotation rate? Let me give you, however, a basic primer here on neutron stars and what are referred to as pulsars. Okay, so to do so, let's jump back up to my previous diagram here. Like so, for the sun as it is today, and then we once again have these values. However, the sun also has a magnetic field associated with it. We will, of course, get into magnetism at a later date. The magnetic field of the sun is what is referred to as a dipole magnetic field. It is shaped like this. Like so, where the magnetic field lines here in red intersect the sun at the sun's surface at these locations. These locations here are referred to as the magnetic poles, and they are offset from the geographic poles here and here by some distance. Let's now go ahead and crush the sun down to the size of a neutron star. When you do, the magnetic field lines that are present here for the sun as it is today, they all get bunched together. When they get bunched together, this then means that the magnitude of the magnetic field strength is much larger than it is today. So now let's go ahead and crush the sun down to the size of a neutron star. So for the neutron star, the radius is 10 kilometers, that's 10,000 meters, and And then we're going to go ahead and calculate, first of all, the rotational period. But before we do, right here now is this really strong, tight magnetic field associated with the sun as a neutron star. Okay, let's go ahead and calculate the rotational rate, and then I'll use that then to describe what happens in terms of an object that's called a pulsar. A pulsar is actually just a rotating neutron star. But for now, let's just go ahead and calculate the rotation rate. Okay, so then therefore we're going to have here the final value of the angular momentum, I omega. It's going to be the same once again as the initial value. This is going to be 2/5 mr squared, 2 pi divided by capital T. And then we would go ahead and use the exact same expression as I did before to calculate then the new rotational period. So the new rotational period, after you do the math, is equal to this, once again. Like so. But now let's go ahead and punch in the new number here for capital R. The radius of the sun is 10 kilometers. And then therefore the period here, as you're going to see, is going to be quite short. Okay, so let's go ahead and do the math. So this right here is 10,000 squared. There we go. And then divide by 7 times 10 to the 8th squared. And then multiply by 30 days once again. When I do, this ends up being 6.12 about times 10 to the minus 9 days. So instead of converting this into minutes, let's go ahead and convert this into seconds. If you recall, there are 86,400 seconds in a day. So let's multiply by 86,400, like so. Days cancels out. So times 86,400, and you end up then with an extremely small period. It's 5.3 about times 10 to the minus 4 seconds. That's about a half a millisecond. About 0.53 milliseconds. And a millisecond is 1/1000th of a second. So ultimately you end up with this extremely fast rotation rate then, and you have this extremely strong magnetic field that is rotating at this rate. This then results in the object being sometimes referred to as a pulsar. Here is a basic description of a pulsar. Okay, so right here is my neutron star with the equator like so, and then here are the geographic poles. So I didn't do this before, but let me go ahead right here and draw in the axis of rotation. So then therefore the neutron star is rotating like this. Okay, and then we've got this really strong magnetic field. The magnetic field lines are all bunched very tightly together like so. And then through some pretty complicated physics that occurs in the interaction between material of the neutron star and its magnetic field, you end up with this huge beam of radiation in this direction and in this direction like so. A lot of this radiation, by the way, is in the form of radio waves. And then let's say that the Earth happens to lie along the line of sight of those radio waves. Every time that those radio waves sweep over us, much like a lighthouse light, for example, we would then see it as a radio pulse. So the first pulsars, as they're called, were discovered back in the late 1960s when a series of radio pulses were discovered by using, for example, radio telescopes. Once again, you have to think of it as analogous to a lighthouse beam, kind of like sweeping over your location. When you look at a lighthouse, you don't see the light continuously. You only see the light when it sweeps over you. So that would be a light pulse, for example. This is the same thing, but it's in terms of radio waves. So kind of think of it like this. Imagine that this stick right here is this beam of radio waves, and then the whole thing is rotating like this, remember, with a period of only a half a millisecond. So then therefore, if we kind of like lie along the line of sight, say like so, as I point the stick towards my phone, every time that the stick sweeps over your location, you would then see that as a radio pulse. Okay, I've posted further information for you about neutron stars and pulsars in today's folder.